One thing that is very important to keep in mind when you're analyzing archaeological data is that no measurement that any archaeologist can make is ever without error. There are always some kinds of errors associated with those measurements. We hope they're small. Sometimes they're actually quite large. And it's very important for us to understand those errors and what to do with them in order to draw valid conclusions from the data that we collect. One kind of error has to do with the precision of the instruments we use to make the measurements. Obviously, if we use calipers, whose smallest increment is 1 millimeter, we wouldn't be able to measure things like thicknesses of flakes and so on to precisions better than plus or minus 1 millimeter, or perhaps maybe half a millimeter if we kind of eyeball the difference between two increments on the vernier of the caliper. If we have a digital caliper that has been calibrated to be accurate and precise within plus or minus 0.01 millimeters, obviously we can be much more precise about the measurement. And if we believe the manufacturer's claims about accuracy, we can also believe that the measurements are accurate. However, it still behooves us to do some checks to make sure our measurements are accurate, because the precision of the measuring instrument is not the only factor in deciding whether our measurements are accurate and precise. It's important to remember that accuracy has to do with bias. An accurate measurement is one that is reasonably close to the true measurement. Precision, on the other hand, has to do with how repeatable the measurement is when we do it several times, and to some extent, that's related to the smallest increment that's on our measuring instrument. One of the reasons we find errors on measurements that are related to the precision of our instrument is that when those measurements are on a continuous ratio or interval scale, there's always an infinity of possible measurements between any two values on that scale. So, for example, if we have two measurements of, say, 1.5 centimeters and 2.1 centimeters, in between those two measurements, there is an infinity of other values. If we use a much better measuring instrument and we decide we can measure to 0.01 of a millimeter on our instrument, two measurements that are only 0.01 millimeters apart will also still have an infinity of possible measurements in between them. So that if we kept getting more and more precise instruments, we would always get a different value for our measurement on exactly the same thing, because we're basically getting better precision, or to look at it another way, a greater number of decimal places on the measurement in a given unit. I say in a given unit for a very good reason, and that's because the number of decimal places that we have depends on the units we use. That is why, instead of talking about decimal places, it's much better to describe the precision of our measurements in terms of significant digits. A simple way to describe significant digits is that they include all of the certain digits of our measurement, as well as the first uncertain digit. So if we only measured something to within plus or minus 0.1 millimeter, that means we can be confident, if we have a measurement like 103.1 millimeters, we can be confident about the 1, the 0, and the 3 that make up the 103, but the 0.1 we're actually not certain about, because the actual measurement could be 103.05 or 103.14. So if we were to get a more precise measuring instrument, we might end up with a measurement like that. So if it could be 103.083 or something like that. So the 0.1 is not a certain digit. So in an example like 103.1 millimeters, the number of significant digits is 4. It includes the 103, the certain digits, plus the 0.1. So all the certain digits plus the first uncertain digit. And when we count significant digits that way, they're immune to changes in units. So if 103.1 millimeters is the same as 10.31 centimeters, but 10.31 centimeters still has 4 significant digits, even though it now has 2 decimal places instead of 1. In addition to accuracy and precision, we should also be concerned with the reliability of our measurements. A reliable measure gives much the same result no matter who makes the measurement or under what circumstances, for example, with different instruments or in different lighting conditions. One way to check on reliability is to compare the measurements of two observers on the same scatter plot like this one. If the results are highly reliable, most of the dots should appear very close to the diagonal line. If, on the other hand, there are any outliers like these two, that would suggest that at least one of the measurers was making mistakes. Some archaeological errors are statistical and result when we make observations on a sample to draw inferences about some larger population. A key feature in such situations is the standard deviation, which represents how much variability there is around the mean, in this case 3.7 millimeters. The standard deviation is the area of a normal distribution that occupies about 68% of its total area. It's generally represented by S for samples and Greek letter sigma for populations. Whenever we make arithmetical operations on measurements that have errors, the error on the result typically differs quite a bit from the errors that we started with. For the following examples, we'll ignore complicating factors like covariance between the variables being measured. When we add or subtract measurements, we start by simply squaring the individual errors. Then we add these squared errors up and take the square root of the result. So, if we had these two measurements that sum to 30.1, we would square their respective errors like this, add those results together, then take the square root of the result. Finally, we'd report the result of our sum as 30.1 plus or minus 4.3. If we're multiplying or dividing, the process is only a little bit more complex. Instead of using the absolute errors, we have to convert them into relative errors. That's to say, the error represented as a percentage or proportion of the measurement. So in this case, the two errors are 28 and 20% of their respective measurements. We square those, add them together, then take the square root. Finally, we multiply this result by the ratio that we determined on the left side of the slide. We can now report our ratio as 0.714 plus or minus 0.246. Alternatively, since none of the digits are certain, we could round off our ratio to 0.7. If you'd like to learn more about this topic, you'll find it useful to read parts of Chapter 1 in my book, The Archaeologist's Laboratory, published by Springer. And if you'd like to be updated when I publish new videos, please click on the subscribe button below. Thank you, and stay safe.